Hello everyone, welcome to this lecture 32 of the NPTEL course on Riemannian geometry. So last time we began in the previous lecture we began our study of metric geometry. So that is the second part of the course, and I introduced this important notion of a geodesic. So let me remind you what that was. So gamma from an interval I in R to M is called a geodesic if it is a smooth curve and satisfies this equation that the velocity vector of gamma is parallel along gamma, right. And note that we also allow trivial geodesics. That means if gamma of t is a constant, we also allow such trivial geodesics. It will be just a matter of convenience, right. So one of the important consequences of the geodesic equation is that if gamma is a geodesic, then the speed is a constant throughout, right. So then I also made a comment about reparameterization, which is an important comment which basically says the following, that if gamma from I to M is a non-trivial geodesic and phi is a smooth diffeomorphism, then if you reparameterize gamma using phi, so look at sigma of S being given by gamma of phi of S, then this is a geodesic. The new reparameterized curve is a geodesic if and only if phi is affine linear, okay, which means that the double derivative of phi is 0. So I left this as an exercise, but maybe since this is such an important remark, maybe let me just hint at how to prove such a thing, right. So in fact if you put t equals phi of S, then we have this nice little formula that if you compute the covariant derivative of sigma dot with respect to this variable S, then in terms of the variable t, it is given by phi double prime of S times gamma dot of t plus phi prime of S squared times the covariant derivative of gamma dot with respect to t. So one way to prove this is you can just directly say that this is the covariant derivative with respect to sigma dot of sigma dot, and then apply chain rule. Or if you are more comfortable with local coordinates, one can just write what this is in terms of the Christoffel symbols and then use chain rule at that level to prove this formula. So this is a good exercise which I highly recommend. Now once you have this formula, then of course if gamma is a geodesic, we have that this is identically 0. Also because we are looking at a non-trivial geodesic, gamma dot of t is not equal to 0 for all t, which means that ds sigma dot can be 0 if and only if phi double prime is 0, right. So in other words phi has to be affine linear. So basically if you are given a geodesic, being a geodesic actually depends a lot on how you parameterize that curve, right. So if you have a geodesic, you can't arbitrarily reparameterize that curve and still expect the new thing to be the newly reparameterized curve to be a geodesic. So this is an important fact to keep in mind, that when you say that something is a geodesic, you are really talking about a parametric curve and not the image of a curve being a geodesic, okay. So this is an important point. Alright, so the main topic for today's for this lecture is to prove a theorem on existence and uniqueness of geodesics, okay. Alright, so here is the main theorem that we'll prove. So for all points P in M and for all right, so for all points P in M, there exists a neighborhood U of P and these numbers epsilon delta positive with the following property. Okay. For all points Q in the neighborhood U and for all tangent vectors at Q whose norm is small. So, these are short tangent vectors at q. There exists a unique geodesic which I will denote by gamma v from minus epsilon to m such that it satisfies the following two initial conditions: gamma of 0 is q and gamma dot of 0 is this velocity, is this tangent vector v. So, the picture is the following: you have your manifold M, you take an arbitrary point. What I am claiming is that you can draw a little neighborhood around this, which I will call u, such that for any other point q and any tangent vector at this point, you basically have a short geodesic that lasts for this uniform time minus epsilon to epsilon. So, the key point here is that epsilon and delta are independent of q and depend only on this point u and the neighborhood point p and the neighborhood u that you have picked. Okay. So, there are two things: once you pick this neighborhood u, then you have a geodesic that exists for all short vectors. So we need absolute value of the norm of v to be less than delta, and moreover the geodesic lasts for a uniform amount of time. Okay. So the shortness of the vector is also uniform, independent of q, and the amount of time for which the geodesic lasts is also uniform in q. Okay. So, as a corollary we have the following: given any p in M, and a tangent vector at that point, there exists an epsilon that actually only depends on the norm of the tangent vector, and a unique geodesic gamma v which lasts for a time minus epsilon v to epsilon v, okay, such that gamma of 0 is p and gamma dot of 0 is v. Okay. So, given if you now fix a point p and a tangent vector at that point, then there is a geodesic that lasts for at least time epsilon v, where this epsilon v actually just depends on the norm of v. Okay. It does not depend on the direction of your tangent vector. Okay. So, how do you prove this from our main theorem? So, proof of corollary. This is a very useful trick called the rescaling trick. So, let me quickly go over the proof. So, the theorem implies that there exists epsilon and delta such that for all short vectors in the tangent space at P, there exists a unique geodesic gamma v from minus epsilon to m such that gamma v tilde at 0 is P and gamma v tilde dot at 0 is v tilde. Okay, where you assume that the norm of v tilde is less than delta. So now suppose you are given this tangent vector v, which could be sort of a really long vector. The idea is to rescale that vector so that it has norm less than delta. Okay, so now given v, let v tilde be given by the following rescaling. So delta by 2 v by norm v. Okay. So clearly one can compute the norm of v tilde, that is going to be delta by 2, which is less than delta. So I can apply my theorem to this v tilde and I obtain this geodesic gamma v tilde. But gamma v tilde satisfies these initial conditions. So this is of course fine, but the initial velocity is now v tilde, right. I want a geodesic with initial velocity v. So what do? You basically again just reparameterize your curve, remembering to do it in a affine linear fashion so that it still remains a geodesic. So let gamma v of t be given by gamma v tilde of 2 times norm v by delta times t. Okay. So firstly remember gamma v tilde lasts from minus epsilon to m, right. So it lasts for a time minus epsilon. So note that gamma is well defined as long as so long as 2 times norm v by delta norm t is less than epsilon, right, because gamma tilde is defined on this interval minus epsilon to epsilon, which means that my t is allowed to vary between so my norm t, so this is equivalent to the statement that absolute value of t is less than delta times epsilon by 2 times norm v. So I can just take this to be epsilon norm v. So gamma is well defined on this interval. Okay. Also gamma obviously satisfies the initial condition that gamma of 0 is p. What about the velocity of gamma at 0? Well, by the chain rule, that is precisely 2 times norm v by delta times the velocity of gamma tilde, sorry, the velocity of gamma of v tilde. This times gamma v tilde dot at 0, but what is gamma v tilde dot at 0? By our choice, that is precisely v tilde. On the other hand, by the way we chose v tilde, this is precisely equal to v, right. So gamma satisfies the required initial conditions and it lives on this interval. So this proves the corollary. Okay, so now let me prove the theorem. The proof of the theorem of the main existence uniqueness theorem relies on the following ODE theorem. So this is the well known so called Picard-Lindelof theorem. So if you have taken any basic course in ODEs, this theorem is proved there, and it is actually a very nice the proof of this theorem is a very nice application of the contraction mapping principle. So what does this theorem say? Let I be some interval in R, okay, and let us say W is some open set in R to the capital N, some Euclidean, some large Euclidean space, right. So now let F with components let us say F1 up to Fn be a smooth function on I cross W taking values in again R to the n, right. So, it has capital N components. So, then given any initial point xi naught in W, there exists an epsilon and a neighborhood script u of xi naught such that the following holds. For all xi in U, there exists a unique family which I will denote by yxi, whose components look like yxi 1 up to yxi n. So, this is going to be a function that is smooth in the interval minus epsilon to epsilon to Rn. So, I also assume that 0 belongs to this interval I. So, yxi is going to be a function on this interval cross on this interval to Rn taking values in Rn such that this is a solution to the following system of first order ODEs. So, if you take yxi prime at t, that is going to be f prime at t comma yxi at t, and it satisfies the initial condition that yxi at 0 is precisely xi. Okay. Moreover, if we set y of t comma xi to be yxi at t, then y is a smooth function on this interval minus epsilon to epsilon cross u. Okay. So, the point is the following: you have this xi naught. I am claiming that you can draw a little neighborhood u around this, so that if you take any other point xi, then there is a curve passing through that xi whose velocity vectors are precisely prescribed by this function f prime. Okay. So, this is so a remark is that in general I will call this system star. Star is a nonlinear first order ODE so it has only local existence, but you still get existence, local existence and uniqueness, right. So, in other words, unlike say for linear first order ODEs like what we had for the parallel transport equation, you cannot extend this curve throughout the region of definition, right. You only get local existence of solutions. Alright, so I am going to apply this to prove our theorem. So, proof of theorem on existence and uniqueness of geodesics. Okay, so there are two issues that we need to tackle. One is we need to write everything in local coordinates so that so we need to write an equation an ODE on some open set in Rn. Okay, and the second point is the geodesic equation is second order. So, in order to use the theorem, I need to sort of reduce this to a first order equation. Okay, and this is a common trick that you must have learnt in your ODE class. So, let us address the first issue now. So, of course, if you want to write it as an equation on Rn, you just choose local coordinates, right. So, let P be our point in M, and let W be a coordinate neighborhood with coordinates, let us say x1 up to xn. Okay, so then if you look at the tangent bundle restricted to W, well, that is essentially just a product of W cross Rn, right. So, I denote this W cross Rn by the script W, by the fancy W, okay, and we use the coordinates y1 up to yn, where n is now just 2n, to be the coordinates x1 up to xn and v1 up to vn. Okay, so these are coordinates on this fancy W. So what do these coordinates mean? This tuple x1 to xn, v1 to vn basically just denotes the tangent vector xi. My notation will be I will denote tangent vectors as x comma v. So, you should think of this as a tangent vector at Tx, right. So, this is simply the tangent vector given by Vi del by del xi at x, okay. So, that means using this tuple x1 to xn, v1 to vn, you can parameterize all tangent vectors at all points on this neighborhood W, right. Okay. So, then also let psi naught be the tangent vector corresponding to the 0 vector, right. So, this is really the 0 tangent vector in the tangent space to at P to M. Okay, so now what is the geodesic equation in these coordinates? So, the geodesic equation, if you remember, is just this, right. For all k, we need to satisfy this. Okay, so of course you are summing over the repeated indices I and j. Okay, but now I want to reduce this to a first order equation. So, reduce to first order. So, the trick always is that you simply set so you should realize that a geodesic x of t traces a path y of t given by x of t and its velocity vector in this fancy W, right. So if I want to write an equation for y, I basically just do this, I do the following. So I simply set Vk of t to be xk dot of t. Okay, so then using this, the geodesic equation is now equivalent to the following system of equations. So xk dot of t is equal to Vk of t, and Vk dot of t is minus gamma ijk of x of t times Vi times Vj of t, right. Okay, so in other words, in order to cast it in the form of my ODE theorem, we simply take these functions f to have the following components. So f is simply given by, so let me write it like this. So f, which depends on x1 up to xn, v1 up to vn, that is given by the following formula. It is simply Vk if k is between 1 to n, and it is simply minus gamma ijk of x1 up to xn times Vi times Vj, okay, if k is between n plus 1 and 2n. So with this, by the ODE existence result, there exists an epsilon and a neighborhood U of xi naught, such that for all xi in this neighborhood, there exists a solution which is unique, which has the form x1 of t, x2 of t up to xn of t, and then v1 of t, vn of t, right, with y at 0 is xi. Now simply take, let gamma of t be the first n coordinates. So this basically traces a geodesic in your coordinate neighborhood W with initial condition gamma of 0 is q, gamma dot of 0 is v, where I am taking my xi to be a tangent vector at q, which is given by q comma v, okay. All right, so then note that I mean U is an open subset of V cross Rn. So by the nature of open subsets in product topology, there exists an open neighborhood U which contains I naught. So, there exists an open neighborhood of P and a delta such that the product neighborhood U cross the Euclidean ball is contained inside, so maybe I will say some delta naught, so that the Euclidean ball of size delta naught is contained inside U. But in these coordinates, this also implies that there exists a delta such that whenever V is less than delta and Q is in U, this implies that the vector Q comma V. So, now here this is the G norm, the vector Q comma V is contained inside U. Okay, so then this implies that for all Q in the neighborhood and for all V such that this happens, there exists a unique geodesic gamma on this interval minus epsilon to m such that gamma of 0 is Q and gamma dot of 0 is V, and this is exactly what we had claimed, right. So, this proves the theorem. Okay, maybe let me end the lecture with the following remark, that if you are given a point P in M and if you are given a tangent vector, we let IV be the union of all open intervals I such that I is an open interval in R, 0 belongs to I, and there exists a geodesic gamma from I to M such that gamma of 0 is P and gamma dot of 0 is V. So, then by definition, because IV is the arbitrary union of open intervals, IV is an open interval of R. Okay, so we call IV the maximal interval of existence of a geodesic at P with initial velocity V, and in fact we get a unique geodesic gamma V on this maximal interval, satisfying gamma V of 0 is P and gamma V dot of 0 is V. Okay. Let me also make another quick remark that if gamma dot of 0 is V, this implies that the constant speed of your geodesic is of course just going to be the norm of V, okay, the norm of course computed with respect to G. Yeah. Alright, so that completes our discussion of the existence and uniqueness of geodesics. So next time we'll start our discussion about the first variation formula. So that really tells you why the geodesic equation is important and how it arises naturally if you are trying to find the shortest path between 2 points. Okay. Alright, so that is it for this lecture. Thanks for your attention and I will see you in the next lecture. Thank you.